Well, hey gang, I see you're ready to explore Newton's laws of motion today. In fact, that cart is a perfect example of all three of Newton's laws of motion.
What? We're just having fun with the cart.
But you're moving, you're pushing, and you're pulling. All three of the things that affect motion. And that's what we're going to talk about today on Science Fundamentals, the laws of motion. Okay, let's think about motion for a minute. Now, if you place a book on a table before you go to bed at night, can you be sure that it'll still be there in the morning? Now, we'll assume no one will take it, or that there won't be an earthquake or some natural event. Will it still be there?
Well, yes, it wouldn't move.
Well, it may seem obvious because we take it for granted that if we place an object on a solid, flat surface, it'll stay there until what?
Until we move it?
Right, until we move it or some force acts upon it. And that's what Newton's first law of motion is all about. Objects in motion tend to remain in motion, or objects at rest tend to remain at rest unless acted upon by an external force.
But things don't just keep on moving.
Why don't they keep on moving? Well, you've probably seen one of these around. People keep them on a desk, or you see them at a gift shop. This is called a Newton's cradle, and they show how energy is transferred to make something move. Now, once I start one ball moving, the energy is transferred to the last ball on the line. The energy goes from this one through all these. It's transferred to this last one and kicks it out. Now, if I take two balls, what do you suppose happens? It sends two out the other side because it's greater mass. You have twice the mass that you did when you just used one ball. And it should go on for a very long time. Now let's think about objects and what acts upon them to get them to move and stop. The balls won't continue to move forever. Why is that, Pamela?
Because they run out of energy?
Very good. They will not continue to move forever because eventually the balls lose energy. As the first ball strikes, energy is transferred down the line to the outer one. It goes through all the middle until it kicks the outer one, and then it comes back and transfers its energy and kicks out the end. Now, this will keep going for quite a little while unless we pick it up and start it all over again. But it goes on a long time. Let's try another demonstration with this small toy car I have here. Now, it has a certain amount of inertia, resistance to movement. In order to get this car to move, a force will need to be applied that's strong enough to get it going, right? A force that's greater than the frictional forces acting on the car, such as the friction of the tires on the surface of this table. Now the force must also overcome the inertia of the car, like that. Now, why does it stop?
Because they didn't have enough force to go any further.
Perhaps. Let's do an experiment to illustrate it. Now, everybody take a car. Red one's for you. There's a sporty blue one for Pamela. A white car for Jennifer, and I'm going to take purple, my favorite. And what we've done ahead of time is we took a board like this, and we put different strips of material on them. And as you can see, this is, what is that?
Sandpaper.
Sandpaper, pretty rough. Then we have newspaper, and this is contact paper. It's pretty smooth. This is wood
Cardboard.
and corrugated cardboard. Now, we're going to have a little race. All right, are you ready for the race?
Yeah.
Are you ready for the big race? Everybody get on the line and start your engines. On the count of three, you're going to let go, okay? 1, 2, 3, go! All right. Now, what happened? Now, the sandpaper obviously slowed the car down the most because it feels like it provides the most friction. But something smooth, like this contact paper, isn't exactly smooth. It only appears that way. It also exerts its own friction, and the car will slow down and then eventually stop. The wheels will encounter friction and slow down, like they did against the sandpaper. And you have a lot less resistance with the smooth surface over here, so it's going to go faster. Now, in a real car, If you keep the gas pedal in a constant position, the car will end up traveling at a constant speed where the force of the engine is balanced by the forces of the friction, the air in the tires. What will happen if we raise the ramp like this?
Go faster?
Yeah, well, we'll see. Let's take this book. Can you put that under there for me, Jennifer? You got it? It's pretty heavy. I got this. Now, we're taking it up considerably. That's a much sharper incline. That's good. Right like that. Now, let's try it again with the cars, okay? You ready? Here's whose car was the blue one. Jennifer, you had the white one. Kaylee, you had the red one. You ready? Now let's try the race again. On the count of 3. 1, 2, 3. Wow. What happened?
Racing the ramp gave the cars more of a push.
Well, it's actually more complicated than that. When the cars are on any surface that is not parallel to the Earth's surface, such as this ramp, gravity is really divided into 2 components. So if we increase the incline of the ramp, the parallel force is increased and the perpendicular force is decreased because the gravitational force remains the same. Thus, the cars speed up. Now, Newton's second law states, when an external force acts upon an object, the object will speed up, slow down, or change direction depending on the mass of the object. Now, as we know, mass is a measure of the amount of stuff or material in an object. In our ramp experiment, we kept the mass constant. That is, we didn't change the cars. We did, however, change the force acting upon the cars by inclining the ramp more, and that made the cars speed up. This rate at which the cars speed up is called acceleration, and it is directly related to the parallel component of gravitational force applied to the car. So we increased the incline, therefore the car's acceleration increased. All right, now Kayla, can you stand up on this dolly for me, please? Very good. Now, by just standing there with the dolly not moving at all, you're illustrating the first law of motion. Now, this is the concept of an object staying at rest until acted upon, and it's called inertia. It's basically an object's resistance to change. Now, Kayla, I want you to jump off of it. I want you to spring out forward and jump towards me. Go! There you go. As you flex your muscles and begin to move, the second law of motion takes effect, and you're applying a force which causes the object to accelerate. And now, lastly, as you jump off the dolly, what happened?
It moved backwards.
It moved backwards. Exactly. This is Newton's third law, and it states that for every action, there is an equal and opposite reaction. Forces always occur in pairs. The dolly has its own mass and inertia. It resisted change until acted upon by a force, and Kayla's jumping off caused to move forward and her feet to leave the surface of the board. Pushing against it caused it to move as well in the opposite direction. Now let's do another activity. Okay, now you've all played with balloons and let them go, right? What happens? They fly around the room, exactly. And do you know why?
Because the air pushes, some air pushes that way and it makes the balloon go that way.
Right. And around, sure. It shoots all around the room, expending its energy. And its energy is the force of the air escaping the rubber bladder, okay? Now, let's find out exactly what happens. We're going to blow this up. Now, we've set up a string on a couple of pieces of upright. You can do this at home with any kind of string. And we have a drinking straw here, okay? Now, we're going to take some duct tape and we're going to attach it to this straw, just like this. I'm still holding on to it. Okay, how's that? Think that'll work? Now I'm going to let go of the end of the balloon, and what do you suppose will happen? Let's find out. 3, 2, 1, go! Whoa! Pretty cool, huh? And here's what happened. Remember, Newton's third law states that when an object is pushed, it pushes back. When the balloon end is held shut, all the forces inside the balloon are balanced by an equal and opposite force. When the balloon is released, there is an unbalanced force at the front of the balloon that causes the balloon to accelerate forward. It's the same idea when a rocket needs to push or thrust to leave the Earth's atmosphere and break free of the gravitational pull. Okay, let's look at our wagon again. Remember, all three laws of motion are taking place here. Now, Pamela, why don't you get on the cart right there, and Kayla, I want you to pull her. Now remember, the cart has its own inertia or resistance to change. Now the mass of the cart is made heavier with the addition of cargo in the form of Pamela. Now, to make it move, you need to do what? You need to exert force greater than the frictional forces and its inertial resistance to make it speed up. Now it'll resist with an equal and opposite force. As you pull, come on, pull it back. Once the cart begins to speed up, you've got it in motion. Newton's second law. When an external force acts upon an object, the object will speed up, slow down, or change direction depending on the mass of the object. In this case, the friction of the wheels and the floor will stop it. Now, as well as Kayla no longer pulling with a force to balance the forces of friction. Newton's first law states that objects at motion or at rest remain in motion or at rest unless acted upon by an external force. And once the wagon is pulled or pushed, what happens?
It's hard to get it started, but once it was moving, it was easy.
Exactly. Why?
Because there was a lot of weight, and when you started moving, there's not a lot because it's moving in one direction. You don't have to use all your force.
Exactly. It begins to speed up. Newton's second law. When an external force acts upon an object, the object will speed up, slow down, or change direction depending on the mass of the object. Also, the cart is sitting on wheels that have balanced frictional forces with the ground. The cart also acts on Kayla as she tries to pull it, and yet the ground is the very thing she can push off of. All these pairs of forces are in play, and they all work together to actually get the cart moving because the pair of balanced frictional forces between Kayla and the cart are less than the pair of balanced frictional forces between Pamela and the ground. And now, what about Newton's fourth law?
Newton's fourth law.
Newton's fourth law says that the professor can get into the cart. Now, if you know enough about Newton's law to try your own motion experiments at home, remember it's always a good idea to get an adult to help you with it. And remember, science is fundamental.